Yeah, good evening, guys, and yep. So today, the goal, as I've planned, according to the syllabus, is that we will learn what is random variable over here, and we'll see that how random variables connect to the, the real life version of probability. I should say the applied version of probability. We'll see it how. And this week we will also devote ourselves to understand the very basic like an idea of CDF and how and why. I don't know if you have read other books, but usually CDF is given afterwards. But I really like to introduce CDF before, because after random variables we go into very distinct objects like, or ideas like discrete random variables or continuous random variables. So the CDF has a very big role to play. In fact, like there's a one-to-one connection with the random variables and CDF. We'll show it, and today and tomorrow, my goal is to teach you this concepts and sew the ideas together so that you can get an overview of that. And also, so the goal you should at this and by the end of this week, you should master the idea of cumulative random variable, cumulative distribution function, and random variables, the basics, and can solve all the problems. Okay. Next week it will be examples, discrete random variables and continuous random variables, and next we will be doing standard discrete and standard continuous. So this is the plan of the next 5 weeks, including this week. So I hope you understood an overview of how we're gonna proceed towards this random variable topic. So why do we need random variable? Okay. So understand that probability is defined very in an abstract way. Probability is defined in terms of probability space. Okay. Which is nothing but an event, sample space, an event space, or and a probability function with certain with certain properties. This is how the probability is defined. Now let's say, but this was not the way of the people. Uh, this was not the way of the people when they try to apply, because probability is after all an applied thing, applied topic. Okay, so its growth was from the applied sense. So we will see that how random variables connect to that applied tinge of probability. So let's say there are two gamblers. Okay, let's say gambler one and gambler two. These two gamblers are there, and let's say the game is this, that they're playing a game together. The game is this, that let's toss a coin. The experiment is this, understand. Experiment is toss two coins, toss two die together. The game is this, that if sum is greater than 24, okay, it's like, sorry, if uh, you get two sixes, I will give you $1,000. And else, like, gambler one is giving to gambler two. Else, gambler two will give $100 to gambler one. Did you understand the game? The game is this, that you toss two die together, or roll two dice together, I should say. You roll two dice together, and the game is as follows: that if two sixes are there, two sixes happens, then gambler one is giving $1,000 to gambler two, and else gambler two is giving $100 to gambler one. Okay, this is the game. All of you understood the game? Yes or no? Now the question is that the gamblers want to understand individually that whether they will play the game or not. What is their probability of winning? Or how do you define winning? Okay, the define winning means that their the gain, the amount of rupees they will earn, okay, is more than zero. If its probability is let's say more than 50%, then they will play, otherwise not. Okay, or maybe their average value they will gain is more than zero, that will gain, so it's expected gain. So these things cannot be described within the boundaries of probability space. Okay, the idea is that how much gain I want, the idea of the amount of money I will get. So this cannot be expressed in the linguistic framework of probability space that we have learned till now. Okay, so Shavi and others who have joined new, like joined, like didn't do the last class. I hope you are quite familiar with what I have taught till the last class. Otherwise, you may get a bit lost. Yeah. Okay, great. So therefore, random variables is sort of, you can see, it's sort of gamifying the object of this, gamifying or making sense to this probability. So let's see how we can do it. Let's try to understand it carefully. So they are saying that, so we have an experiment. So let's do whatever we know. We have an experiment E. So with that experiment, we have to roll two die. The sample space is nothing but 1, 1, 1, 2, dot, dot, 1, 6, dot, 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 6, 6. Okay. And the probability, let's say, we define the probabilities like this, that probability of each I comma j is equally likely, is equal to 1 by 36, because it's like classical probability definition, I and j belongs is less than equal to 6, greater than equal to 1. So this is the definition of the entire probability space. Okay, I hope you understood. All of you understood the definition of the entire probability space? It to define like this. Okay. Okay, great. So Shavi, did you understand this? Great. So yeah, I am sure others must have understood because they have been to the classes. So yep. So this is the definition. This is what we know from this. But they want to define like the game out here. Okay. So how to gamifying the subject of randomness. So that's where the random variable definition comes. Okay. So understand what's happening. That if it hits two sixes, then $1,000 our G1 is giving to G2. So the idea is that, you know each of this sigma we can assign a value. That's the idea. Okay. So let's say, so what we do is that let's say we want to understand. Oops. Let's say you want to understand G. One second, one second, one second. Let's say you want to understand this G. The G is the gain of gambler one. Okay. So the G is telling that, one second, guys. So G is the gain of gambler one. To understand how the gambler one will, you know What will the gambler want again? Let's understand the game. So if it's 6-6, then gambler one is losing minus 1,000 bucks. So understand, if it's 6-6, if the output is 6-6, the gambler one is losing. Okay. So G is minus 1,000. If it's rest, whatever the rest happens, the gambler one is always getting 1,000 bucks. So I comma j, G is equal to 100 if I is not I comma j is not equal to 6. Okay, I comma j is not equal to 6. All of you understood this? Yes or no? Please tell me. Did you understand this definition of G?
Please explain it once again.
Great. So now, what is exactly happening? To define this G, you're actually doing but nothing, assigning a value to each of this. So how is this G defined? The G is a function, therefore, from the sample space to real number line such that the G is defined like this. The G is defined like this. The G of xy or ij is defined like minus 1,000 if I is ij not is equal to 6 and 100 otherwise. And this is what random variable is in like the is defined as. It's a function from a random variable x is nothing but a function from the sample space to real number line. Because we want to measure something, we want to gamify the probabilistic event. We want to measure something by this random variable. If you want to try to understand the relationship of this random variable, like a probabilistic experiment with a real life scenario, we need to define it by numbers. This number is given by this real number line. X can be anything. So therefore, from this motivation of this gain, we are defining a random variable from this ij. It's nothing but a function of sample space to real number line, right? It can be anything. If the game changes, let's say the game changes that it should be 2,000 bucks, then it will be minus 2,000. So the experiment remains same. The point is that experiment can remain same, but the game can change. Hence, the random variable remains same, but the gain can change always. Okay, the gain can change always. So the experiment can remain same, but the random variable can change according to the situation demands. So that's the core idea of the random variable. Okay, all of you understood the definition of random variable. Random variable is nothing but a function from the sample space to the real number line. Also understood the definition of random variable. Great, great. So random variable is defined from the sample space of the real number line. It is modeling every real life scenario based on an experiment. Okay. So random variable is a connection with experiments to real life scenario. Chance experiments to real life. Okay, coming back to the next portion is that, okay, we have defined the random variables, but what to do with these random variables? Like, what is our goal? This x. What to do with this x? What's like, what we will do with this x? It's a function. Then what? Like, there should be a purpose, right? So what's the purpose? So they thought that the purpose of asking like questions like, what is the probability that x will be positive? Let's say they wanted to answer questions like this, or what is the expect average value of x? Average value of x. So what is the meaning of average value? Can we say something like that? So they want to ask questions like this. So therefore, the fundamental questions of random variables are related to the fact that number one question that you will see that it's related to the fact that we are interested in objects like probability x belongs to a certain, so x is taking values in real number line, right? So if you generalize this idea, we're interested in the fact that we're trying to understand or find the probability that x is belonging to a subset a good subset A, I should say, of real number line. A good subset A. The probability that x is belonging to a good subset A of real number line. This is the generalized thing. If we can answer this, then we can answer this, right? Similarly, average value will see this is something to do with moments of random variables. We'll see it's something to do with moments of random variables, okay? So we're trying to understand the behavior of x. So this is in some sense like our descriptive behavior. This is in some sense a theoretical behavior, okay? Like going to the very core of it. And there's a connection between that that is called moment generating function. We will do that. So what is the core idea of learning from here? So understand what are the questions we want to discuss. So understand the very goal and the thinking pattern of human beings, okay? They started with this question of connecting probability, the experiment to the real number, real life, and they defined probability like random variable in the process. And after the defining the random variable, they ask questions that what actually they're interested in. They're interested in the average gain or the probability that or the chance that they will win. So this leads to the question. There are two questions it's leading to. Number one question it's leading to is that probability x belongs to A type question, and number two questions are moments question. Okay, so we will see that this probability x given to A question is nothing but an equivalent aspect of CDF. Okay, a CDF defines this, and a probability, if you know this, you can define the CDF. Now, based on the property of the behavior of the CDF, it's a function. We'll say that we do different type of random variables. One is discrete, one is continuous. Okay, and then we individually learn them, understand them. And in moments, we will see that it's a general thing. Of course, they are defined in terms of discrete and stuff, but it comes later on. But they are general. It's like describes the descriptive behavior of the random variable. Okay, because they want to understand. Don't want to understand the CDF. Okay, it's too much information for them to play the game. They're understanding basic aspects. How much I'm going to win? What is the average value of winning? Okay, what is the what is the interval between which I will be staying on average? So these are the questions they're interested in. So it's like a descriptive part of the random variable. It's not entirely describing it. It's not the entirety of the random variable. It it discusses a part of the random variable. It explores a part of the random variable. While CDF explores the entirety of the random variable. Okay, moments explores a part of it, but both are important. Okay, so that's why we learn it differently, but this is the entire plan how the whole story of random variables evolved. Okay, all of you understood this, guys, where we are heading towards the goal and where we are focusing now. So in the first part now we will focus on some examples of random variables. I will do this. After that, we will focus on understanding this case. Probability x belongs to a, and hence discovering the CDF on that part. Everyone clear with this idea, guys? Any questions on your part? So John, hello John, hi. Can you hear me? Okay. Others, did you understand this whole idea? Great. Because these are small philosophical and aspects which you should know and the story behind it. Otherwise, it will seem very dry, not a juicy way to learn. So that's why I am sharing this with you and asking you. Shavi, did you understand? Great. I hope all of others understood too. If not, please raise your hand. Okay. So therefore, I will do now some examples of random variable. So examples of random variable includes, let's say, you have a lot of different examples actually. We can have a lot of different examples. So I already gave an example to you that like gain wala example. You can also have this kind of example too. To understand, you must have on this side a sample space, an event space, and a probability space, a probability function. The probability function can be different, okay? And this is connected to all of this. And from here, you're connecting to the real number line by this random variable. So let's say you don't know, like let's say you don't know how the uniform random variable is all about, but yeah. So let's say so I already showed you. So let's take an example. Let's say the general kind of random variable. So let's take an example of random variable which take into all discrete values. It means that whatever the experiment is all about, okay, x, whatever the experiment is all about, x is somehow changing it to this set. R is defined as it only take a few values like x of something. X, the only values x take, the range of x is equal to range of x, not the codomain. The range of x is equal to nothing but x1, x2, dot dot dot. Yeah, these are the real number values it takes. Okay, it can be infinite, it can be xn, okay, anything. So understand, we'll learn this in discrete random variable. We'll learn this in details in discrete random variable that what is the goal of this. But let's do an example that uh, we are interested in what? We are interested in probability x belongs to A, right? A is a subset of R. Now, the things you can take, the values it's taking are subsets of this set, the range, right? So A is a subset of the range of x. So therefore, you can see by the law, it's taking, therefore, if you can define individually probability x is equal to xi, automatically you can find the probability using the size law that, so remember, understand this. This is not a, understand this very carefully. Understand this very carefully, okay? Very carefully. This is something where people goes wrong. X is not a something, understand this very carefully, okay? So here is a sample space. Here is the x, and it's going to the real number line. So each point in the sample space is going to a real number value, okay? Each point. So understand that, let's say it's taking values in a good set, in a good set A. Let's say this is a good set A. The probability x belongs to A is actually does not mean anything. Okay, understand this very carefully. X probability belongs to A does not mean anything. Or x probability is x is equal, x takes the value as x1, or the gain takes the value 1000. Okay, this does not mean anything actually. Like probabilistically doesn't mean anything, because probability is a function from the event space to the 0, 1. So this, the definition doesn't make sense. Okay, so therefore first we need to define probability x belongs to a set A. X is a real number, real valued function. So this is nothing but probability. Yes, SK?
Sir, could you repeat the last part? I didn't get why the definition doesn't make sense.
Probability is a function of the event space, right?
Yeah.
To 0, 1. But when we say probability x is equal to, let's say 1, x is equal to 1 is not an element of the event space, right?
Right. It's a function, so yeah.
So therefore it's defined as, probability x belongs to A is defined as, understand this A value.
Excuse me, sir.
Yes.
So I could not understand. I mean, how the probability of x. I mean, why the definition is so abrupt. I mean, the
Okay.
probability.
So
Yeah.
let's say I tell that I ask you to find the probability with this experiment, okay? Ask you to find the probability that G is taking the value 100, okay? Now G is taking the value 100. This is not an event. Like probability is only defined on the event space, right? So
Yes,
this
sir.
is not an event. So this the G is equal to 100 is not an event, but it is related to an event. So what we do is that instead of doing probability x is equal to A, what we see is that the corresponding the set from where this A is going to that A, like the corresponding set we see, which is going towards, which is taking the value A under this function. So in this G is equal to A example, so G is what? G is a function G is taking values, let's say G is taking, so we want to understand that, let's say the probability G is equal to minus 1000. Now this does not make sense. This is not an event at all of the experiment, right? But this is equivalent to, this is defined as, we can define this as probability G is equal to 1000 if and only if it takes the value, like it's taking 6,6, right? So it's equal to the event, it's probability of the event 6,6. Understand this very carefully. It's probability of the event 6,6. If I ask you to find probability G is equal to 100, it's nothing but probability, it's 1, 1 or 1, 2 or 1, 3, etc. Except the 6, 5 dot dot dot. This set. So we are defining the probability of this random variable, the value text, okay, equivalent to the probability of the corresponding set that gives rise to that value 100, or that set that gives rise to the value minus 1000. So the corresponding event, a subset of the sample space, is actually giving rise to that 100 value, the set of all the possibilities. All the here it's 6 comma 6. Here it's all the things except 6 comma 6, all the points. So probability of 100 is nothing but the probability of this set, because this is a subset of the sample space, and it's an event therefore, and therefore we are being able to find the probability of that. So therefore we say that probability of x belongs to a set A is nothing but, it's defined as x inverse of a. Now this is a function x, this is a real number line. So x inverse of a means exactly this set, the set of all x. X inverse of a is defined as the set of all x such that x belongs to the sample space, and or all a such that a belongs to the sample space, and x of a. That means that point in the sample space is going towards, is taking values in a, the set A. Did you understand, all of you? Yes or no?
Yes, sir, I did understand the whole part, but please just explain this last line, x inverse A.
Yeah, x inverse of a or set A. This is the set A. This is x. So x inverse of a is nothing but that subset of the sample space. All the elements, like all the elements of the sample space which goes inside, like which goes to the, which checks the values inside a when x is like when x is going, like when x is acting upon that. But here example, all the elements 1 1 except 6 6, when x is acting upon that, is going to 100. Hence x inverse of 100 is nothing but this set. This is nothing but x inverse of 100. The set of all values in the sample space which takes the value 100, or which takes the value inside a can be a big subset also, when x is acted upon a. Where did you understand, Swati and others, all of you? Yeah, SK.
So, but for this, A should belong to
The real number
good.
line.
No, sorry, small a. Small a should belong to good subsets of uh, what?
Yeah, this x inverse a is also a good subset. It must be a good subset.
Yeah, I mean, a small a should be subset of E, right? Otherwise, it
What is
won't
an
be.
element? It's not a subset. It's set of all elements a. This is a. Set of all elements a such that when x is acted upon a, it goes to this set a. This big set A.
Yeah, but to assign some probability to small a, it should be set of E, right? Capital E.
Yeah, so therefore probability of x belongs to a is nothing but x inverse of a. So x inverse of a is nothing but an element of the subset of the sample space, right? And it should be, it's a good subset. It can prove this. But it's a
So,
subset
but
of
we are
sample
not
space, right?
yeah, but we have to
Yeah.
specify that it has to be subset of E, right? Or is it okay if we don't
It's
specify?
right? It's all the elements of A all the elements A. So that A is an element of sample space, and A is going to inside A, capital A. Now, therefore, A is a one subset of the sample space, right? The set of all such A. The X inverse is therefore subset of sample space, right? Because they are made up of elements of some sample space.
Yeah.
Did you understand?
No. I am confused between E and
What is E?
it is a. I'm confused. What is E?
No, please, like, I am here to clear your confusion. Please go ahead.
So can you show the previous slide? Yeah. So sample space to E. E is good subsets of sample space, right?
Yes.
Which we assign probability. So, right. So small a should be a subset of E, right? And we just can't say that
Small
small a.
a, small a is a set. Small a is nothing but an element. Okay. X inverse A are elements of the sample space. Elements, individual elements of the sample space. Outcomes, such that the random variable takes those outcomes inside A, capital A. For example, 1 comma 1 is the A here, 1 comma 2 is A here, 1A, 1 comma 3 is another A. These are all elements of the subspace, that is the entire subspace, such that each of these, x of each of these values go to 100. So together they form a subset of the entire sample space and hence a good subset. Did you
Okay,
understand?
so we don't have to specify it separately that it is a subset of good set. I mean, a good subset of sample space.
It will
To say
automatically become. So this, I am just, I am making things simple for you. These are related to something called measure theory. Okay, I'm not going to do that. Okay, because
okay,
it, but like it's called measurable function. So as I told, A is another good set of R. If A is not a good set of R, then we cannot take A, like then X inverse of A will not be a good set of sigma. This sample space. Okay.
okay, I didn't get this. The last part I didn't get this,
So
but whatever you
we
told
are
before, I got that.
we have told that X must belong to the X is a subset of range, right? A.
Yeah.
There is another condition, A must be a good subset. Okay. So what is a good subset? Let's not go into that. But if X A is not a good subset, X inverse of A will also not be a good subset. But since we assume that A is a good subset and we're taking its X inverse, hence it will be also a good subset. It's like related to the measure theory, but we are not doing that. So you have to
Okay.
assume.
So somehow it is known that it is a good subset. So that's why we don't have to specify.
Yes. All of you understood this idea that probability of a set X belongs to a set is nothing but it defines the probability of X inverse of A. X inverse of A is the event which goes to A under the image of under the function X, under the random variable X. The set of all the elements which goes to A. Because now this is an event and hence probability is defined on that. So therefore X belongs to A is nothing but this. Okay, all of you understood this? Yes or no? Great. Superb. So therefore, we have defined that we need to find x of x inverse x, this we need to find this. Now naturally for discrete, the where x takes values x1 x dot xn, we'll see in discrete random variables if we just define the probability x takes the values x1, x takes the values x2, or dot x takes the values xn. Okay, that will suffice. That will suffice. So also remember we define this as P1, this defines as P2, and we generalize this. Just like the, you know, just like I gave an example of probability space, right? Similarly. And we'll see that probability X, it's like this is a new sample space in some sense. This Xi are a new sample space. Okay. And each of them has a probability on it. So that's kind of really interesting. It's like when we tell an X is going towards in R, it means we are taking the sample space to be the range of So when we say this, what happens is that from sigma we get E, from that we get P, right? Now this is going towards R, rather the range of X. Therefore, this becomes, the range of X becomes a new sigma dash. Okay, and E dash becomes a new set of all the events. And this P dash becomes a new probability function as defined as above. Like P of X belongs to A is nothing but probability of X inverse of A. And E dash, you can easily understand that how it's like all the good subsets of range of A. Do you see the change in sample space, guys? This under the random variable goes to range of X is a new sample space. The events become different. Instead of all good subsets to this, and the probability as we defined is changing like this. Therefore, the random variable is nothing but changing one experiment to another experimental format, which is easier for us to handle. And we can apply the probability theory over there. Did you understand this, guys? Yes or no?
So how's the range of X equals to the dash of
It's
probabilities
like a
in
new
sample
sample
space?
space, okay? It's a new sample space. X can only take values x1, x2, xn, let's say. Okay, so let me give an example. In the first one, we have the sample space to be what? 1, 1, all these things, like till 6, 6, right? By the X, the new sample space turned out to be what? Just minus 1000 and 100, right? The sigma, the E was nothing but all good subsets of the power set of X, the power set of this. Here, now since each of them goes to times 1000, so therefore the power set is nothing but this two. Pi, the power set of this is a sigma dash. Because we're interested, probability X belongs to A. A is nothing but a subset of this, right? X belongs to A. A is a subset of, is a good subset of this. So therefore, this X belongs to A is nothing but, in some sense, probability of A, you can say. Like, therefore, if we define this as like the event space, new event space to be the power set of this, and the probability, you can see here was P, and there under X when it goes, we already defined that it becomes P dash of A, right? Or P dash of X belongs to A. It's nothing but its probability of X inverse of A. So it's nothing but it's connecting under X, it's connecting the random variable, like it's making a new probability space altogether. So probability X belongs to A, it's sort of equivalent here to probability of A in this P dash of A, okay? And it's equal to P of X inverse of. Did you understand, guys? Did you understand this? It's making a new sample space in some sense. Because you see, this is nothing but a discrete framework which you already done before, right? On the real number line. So therefore, it's nothing but it's changing the sample space altogether. It's reducing down the sample space. And hence the event and hence the probability. So everything is getting changed. Did you understand, all of you? This one? This is very important. So therefore, in some sense, to understand a random variable, if you can understand the probability on a real number line, where sigma is a real number line, any sort of the real number line, we are done. That's the idea. Because X is taking any sample space a real number line. So therefore, the goal turns out to be, we want to understand when the sample space is just real number line, and hence how the probability will happen. Okay, that's the basic idea. That's the basic idea. So, and hence from here we go into something called cumulative distribution function. So we are interested in probability X belongs to A. A is a good subset of R. is a good subset of R, right? So probability, to understand, we have defined it before. The idea is that any good subset, this is a fact, you can assume this. Any good subset can be expressed as union and intersection of this type of sets, this set. Any good subset can be expressed as union and intersection of this type of set. This is a fact. Okay. Whether the subset is discrete or not discrete, it does not matter. It's countable union. Like infinity is possible, finite or infinite. This is a fact. I've already told this before, but this is a fact. If I assume it, and I've given you examples also how this is true. So any good subset is nothing but express the union and intersection of minus x. So therefore, what we will do is that we can find any x. So therefore, a random variable x is equally can be identified with probability x belongs to any set A, for all A set belongs to the, you know, the event space. Now this is equivalent to, we say that probability of x belongs to minus x to x, minus infinity to x. Only this sets where x is a real number. Yes, SK?
So what do we mean by counting infinite?
That you can count like natural numbers, 1, 2, 3, dot ऐसा.
Oh.
So it's like you cannot take like, yeah, it's like you can just count. It's like I from 1 to n. It's like what I meant like that. Okay, 1 to infinity. Okay, that's what is countably infinite. So let's not go into that. Okay, it will be, you can read this from Bertley Sherbert or Stephen Abbott. What is countably infinite? But it's like it's 1, 2, 3, dot infinity. ऐसा. It's like discrete format. So therefore, to identify a random variable, it's an if and only function with probability x belongs to any subset, any good subset of R. Now the fact tells you that this probability is equivalent to asking probability of just this sets. X belongs to minus infinity to x for all when real number x. Okay. So therefore, it turns out to define a x random variable, we are just interested in this probability. And you can see this is nothing but a function of x, a real number x. And this function, therefore, was defined as the CDF of x, the cumulative distribution function of x, like this. This is defined to be the CDF of x. Okay. It's cumulative distribution. Why? Because x is a one-to-one connection. I have shown you that. The goal is to find probability x belongs to any subset A, and therefore any subset A can be written as union intersections of this subtype of subsets. And therefore, this set of subsets is nothing called, just one variable is their x. So therefore, it's like trying to minimize the variable, okay? As I told on the first day of probability. And hence, this is nothing but defined as probability. This nothing but defined as a CDF of x, okay? So therefore, understanding a random variable is boiling down to understand the CDF of the random variable, nothing more, okay? All of you understood this, guys? Yes or no? Great. So therefore, the next part is, this was the introduction to random variables and CDF. Okay. Therefore, the next part is focused on understanding the CDF of a random variable. So, so CDF therefore is nothing but a function from what? It's a function from where? Function from R to R. Okay. Where f(x) of x is defined as probability x is less than equal to x. Rather, it's equal to probability x belongs to the set minus infinity to x. Okay. This is the definition. Right. So this is the definition of CDF of a random variable x. Right. Now, yes, SK.
So we are writing that capital R as codomain only, right? Not range, because range of CDF will be only from 0 to 1.
Yeah, yeah. So now I will be defining the properties of f. Don't worry. So yeah, as SK has mentioned, so yeah, I will be. So now the goal is that, so this is a very specific function. Now, therefore, the idea is what? X has a one-to-one relationship with its CDF. Yeah. Therefore, once we understand f, we understand x, and vice versa. Therefore, the most of our, our understanding will therefore focus on the properties of fx. Properties of fx. Okay. And this will take some interesting time, amount of time. Properties of fx. Or cumulative distribution function. Okay.
So,
Yes.
can we define the cumulative distribution functions as the probability of all the good subsets in on a real number line?
No. It's a probability of x is nothing but, see, we cannot define as all the good subsets. That's too many of good subsets. So what we can, using this fact that any good subset can be used as the union intersection of this. So what we can do. So we can reduce it down to only just bare minimum what is needed to this type of sets. And if we need to find a very complex set, what you know that using this type of sets you can find that. Hence you can use the PIE, the principle of inclusion exclusion, and all the laws of probability, properties of probability, and this FX to find out any good subset of probability. Do you understand? Let's say you find out that it's minus infinity to 2 intersection minus infinity to 2.3 intersect union minus infinity to 3, and let's say something. It goes on. Now using the law of probability, you know how to calculate probability A intersection B, how to calculate probability of A union B. Okay. And all using these things, you can actually find out this in terms of like this entire set in terms of this. If it's like clubbing up all the values of this kind of set. Therefore, you can find the probability of any good set using the probability of this types. That is this probability of this type is nothing but f of x. Okay. Therefore, we are just trying to find out. So it's like we are doing the bare minimum of the bare requirement. Okay, we are trying to understand the bare most, like it's like understanding the basis of a linear, of a vector space. Did you understand, Swati? Is your question clear, or you need more explanation?
So if you can provide a little more explanation, that will suffice.
Yeah, please tell me which is your doubt.
So, what are you trying to say is कि the union and the intersection of minus infinity to x is the good subsets of
X,
all. I
X
mean,
is variable over here. Okay, so we are trying to define the scalar distribution function as a function like it's X is a variable over here. So if you put in any X, you can find out the probability. Okay, so f is nothing but a function from the real number line to like real number line where X is, yeah. So I'm not getting what's your doubt.
s- mi- the good subsets are the union and the intersections of this minus infinity to x.
X type of subsets. So X, there are infinitely many subsets. If you put different X, you will get a different set, right?
Yes, and for each such set, we can find CDF of it.
So no, it's like for if you put in each set as X, the value of X, we find as that value of the CDF. Like it's a function, so it's like it's taking X. So it's like CDF is taking X, giving this, and finding its probability. So this entire process is, so it's taking this input. The entire process is less. So it's like this. The CDF is doing this. This is the function of CDF, and this is the output. This will be a 0, 1 interval since it's a probability. Did you understand? It's taking in X, it's making this infinite set, and then finding its probability out. For each X, we get this probability. Did you under what is your doubt? Can you be more specific?
So I think I'm being confused.
Yeah, tell me
Ki-
what your confusion is all about.
So all I want to say is कि the union and the intersection of all the sets like minus infinity to
Not
x.
all the sets, some specific sets can give any good subset. That's the result. That's a fact we are using. We don't know that's like you don't know the proof, but that's a fact.
Yes. So for any such subset, you can find the CDF by putting the value of x.
No, no, we cannot find a like the CDF is just used to find probabilities of this types. The use of CDF is to find probabilities of this type, nothing more. So it's like this. Let's say you want to find probability X belongs to a random subset A. Now you find it, therefore, the first step is that you find it as union intersection of good subsets, like of this subsets of like this. Could be. You don't know what are these values, but yeah. Now this can be written as summation or subtraction of probabilities of this format. Xi, or not exactly like this, but it can be written as summation and summation of that, okay, all of those. Okay, because yeah, you can write that. So it can be expressed as function of some function of the probability of, let's say, minus infinity to x1, comma probability minus infinity to x2 of each of these individuals, because each of the probability of each of these sets can give rise to the probability of this. Now, to find this probabilities, individual probabilities, we need the CDF. So it's like f of the this. So we can go back and find this out. So the goal is that once you know all these values, automatically you will find this, right? That's the bare minimum that we need. So our goal is to find all these values. And this all these values, we need to define the CDF like this to understand, know the all these values, because X is a continuous, it's like continuous, a real number line. So it's a function from the real number to real number. Did you understand?
Yes, sir. Thank you.
Sure.
Yes, sir.
Great. All of you understood this clearly? So therefore, great. So therefore, therefore, our goal therefore is to understand what this type of functions. Where the goal is to understand the properties of these functions. So let's understand it one by one. So we'll explore that how we can understand which function is CDF or not. The properties of CDF, which functions are CDF or not. Okay, so therefore, let's understand its properties. So often in books you will find out that CDF is defined when you are defining a continuous random variable. Okay, but I don't think it's very intuitive enough because it seems like CDF just it came down from somewhere, just from top, out of nowhere. Because discrete random variable can use PMF, and suddenly we move to CDF. This is like so it does not create a story out of the theory. So you should learn like a theory, like a story, because a story helps to remember things. Okay, it's important. That's how you enjoy learning. Okay, so first of all, let's see. As SK has told, CDF is nothing but another probability function, like sub probability function. Therefore, CDF is always between 0 and 1, right? Since you can understand, because fx is a probability. All of you got with this idea? All of you got this idea? Yeah, very basic stuff. Next idea is fx is non-decreasing. So why we are understanding this? Because since fx has a one-to-one connection in the random variables, the behavior of fx can give an insight of how the random variables can behave. We will see exactly that's how discrete random variable and continuous random variable are defined. Okay. So fx is non-decreasing. That means if x2 is greater than or equal to x1, this implies Now, why is this true? Let's try to understand this. It's very easy. So we will prove each of the properties. Why? Because these other properties helps you understand probability function better, which is the most important idea. So x2 is greater than x1, right? So f of x2 is this, therefore nothing but probability x belongs to. So x belongs to x is less than or equal to x2, right? So therefore you can write this as probability x less than x1 disjoint union of x less than or equal to x2 and greater than x1. It's equal to, by the size property of probability, each of these are event, right? This is nothing but an event. X inverse of this set. So if you want to this is actually a step down. Whenever you're writing this step, this is equivalent to, if you want to just make you understand, this is equivalent to the statement like probability x inverse of minus infinity to x1. This is an event. Disjoint union of x inverse of x1 to x2. These are all events, okay? These two are events. So it's actually defined like this, but we don't write this step, okay? Because we understand it. But remember, this is not an event. The definition is an event. So they can ask you this, okay? In interviews, or this is a very core understanding. But anyway, so directly we write this step that it's nothing but probability x less than or equal to x1 plus probability x1 less than or equal to x2. This is nothing but what? F of x1 plus probability. Okay. So therefore, what do we get? We get that f of x2 minus f of x1 is nothing but probability x is less than or equal to x2 greater than x1. So we assume that x is actually greater than x1, okay? So therefore, you know that this is greater than or equal to 0, right? Because probability is greater than or equal to 0. We have found out that. We know that. Therefore, this implies that f of x1, f of x2 is greater than or equal to f of x1. So it's non-decreasing in nature. All of you understood the proof, guys? All of you understood the proof? Great. Swati, did you understand? Neha, are you understanding?
Sir, in this definition, the
Yeah.
event is x inverse minus infinity to x1, right?
Yeah. Yeah.
This is the event.
Yes.
Okay.
But we are not we are avoiding that step, okay? The reason is this, that let's say here are two disjoint sets. Its inverse must be also be disjoint, right? The events. Why? I mean, these are all the elements that goes to this set, and these are all the elements that goes to this set. Now, if there is a common part, there is no common part here, right? Hence, there will be no common part here. Let's say there was a common part here. Let's say there was a common element here. Therefore, this element must go to here, and this element must also go to here, and both are the same value. Like this single element has an element which also must be here and here, right? And hence their intersection will be non-null. Something will be there, but it's not that they're disjoint, and hence uska images, pre-images will also be like x inverse must also be disjoint since they are disjoint. Inverse image is also distant. Did you understand, Swati?
Yes, sir.
So that's why we skip this set. It's actually the like whatever it's happening here, it's behaving exactly like another event set. Like that's the idea. Great. And okay, so then comes a bit of limit x tends to infinity f of x is 1. We can also build up with light as f infinity is equal to 1. And limit x tends to minus infinity fx of x is equal to minus 1. Sorry, it's 0. I'm so sorry. So what is meant by this? What is meant by this? So let's try to understand this. This is very interesting. So limit, therefore it's asking what? Limit x tends to infinity. Probability f of x. Yeah, someone has allowed yeah, iske.
Yeah, sir, I think it should be 0 instead of 1.
Yeah. I'm sorry. Okay. Next is going to infinity. Right. So do you remember the continuity results of a p? The continuity results of p. So understand that this set is, let's say x is going to infinity. So this set is a subset of something more than that. Let's say we start with x and x1. X1 is greater than x2. Subset of, and it's an entire subset of the real number line. Okay. It's minus infinity comma infinity. That is a real number line. So therefore, when you have this, limit of this is nothing but probability what? Limit goes inside and x belongs to this. And this is nothing but, it turns out to be that x belongs to the union of all this. That is R. By the continuity, this happened by the continuity principle of property of, we have told this, right? Property of probability. We have already done this like as a property of probability in the first class, axiomatic class. And x always belongs to the entire real number line. It's nothing but always 1 because x can take only real number values, right? All of you understood this, guys? Yes or no? Did you understand this? If not, please tell me. Okay, there seems to be some doubt. Please tell me if you have not understood this. Please raise your hand. I don't see any yeses in the comments. Yeah, or is it my net trouble? Did you understand this, guys?
So please explain this once again.
Yeah, why are you shy to tell me? You should always tell me that, ask me to explain once again. So Which step didn't you understand? This step you
So
understood?
there's continuity property of probability. I mean, how do we implying it on this?
Do you remember the continuity property? So A1 is a subset of A2 is a subset of A3 dot dot dot, right? So it was that at limit n tends to infinity, probability of an is nothing but probability of limit n tends to an. This was a continuity property, okay, of P. So therefore this happened, and now yeah. So why it's doing for continuous variable? Because if x, if we can show for any sequence going to infinity, then it's true for, it's the limit also true, right? So whether for any sequence going to infinity, this is the same answer for all sequences. So this is a sequence, this is a specific sequence, right? X1 greater than equal to x less than equal to x2. It's going to infinity. So for every specific sequence, the limit is turning out to be limit x tends to real number, x belongs to real number line. Why? Because the limit n tends to infinity, the all the n's is nothing but the real number line, right? It will go to infinity. That's natural. That's real number line. So therefore, it's nothing but probability x belongs to R, which is 1. You can understand this? Or do you want more explanation?
No, sir, I did explain. I did understand this. Thank you.
Okay, what about others? Okay, Shabi told yes. What about others? Great. So similarly, the limit of using the opposite property, x tends to infinity, x tends to minus infinity, f of x is nothing but limit x tends to minus infinity, probability x less than equal to x. So you can see it's nothing but probability of limit x tends to minus infinity, x less than equal to x. So it's like the intersection part, okay, a decreasing part. All these are decreasing, right? Then, so therefore, it's nothing but probability limit x intersection of all this is nothing but phi, right? The empty set. Like we keep on decreasing, so it's phi. It's always probability zero. So therefore, we get these two properties by the continuity principle of probability. All of you understood this clearly, the continuity principles of probability? Any doubts? Any doubts? All of you understood this property, guys? The second property? All of you understood the entire three properties? Okay, thank you. So, SK, what about others? Great. So I will keep the today's class till this point of time. Tomorrow I will be doing more detailed stuff like the right continuity of the cumulative distribution function and the graph of it, and from that graph how we can understand different behaviors. Okay, we'll explore this right like this type of functions more and tomorrow, and we'll understand more examples, and yeah, that's it. That's what we'll be doing. And yeah, so that's the idea I have on my mind. Yeah, that's it. So yeah, so let's keep the class over here. Good night, guys, and I will see you tomorrow. Do you have any doubts regarding today's class? John, did you understand that?